Okay, welcome to Chapter 17. This is electric fields, and this in the new chapter, so first section of Module 6, okay, is a green cover, so you can keep going with the colour theme and we'll work off that. So electric fields, gravitational fields and magnetic fields leads us into research on particle physics, and it's also very useful in medical physics. So there's kind of a theme running through a lot of this as well as the last one. Hint from the chapter title that I've just shown you, it's actually to do with electric circuits, but it's all to do with fields as well. If we go back to our starter a second, why do charges move? Because you stick a battery on a circuit. Well, the battery is miles away, and yet electrons in a far, far distant part of the circuit will start moving. Why? Because of electric fields. So we're going to start looking at the reasons electric charges move. It's the reasons atoms hold together. It's the whole lot. And over here is Monsieur Dufay, or the work from Dufay and Coulombs, the French people who, unfortunately, got the symbol the wrong way round. We could blame the Americans as well. They're part of the story. So, what are we looking at? Basically, we know a bit already. We know the idea of circuits. We know the idea of gravitational fields, and that's one of our biggest things that we can do right at the beginning. This study here will help you understand electric fields, and understanding electric fields will help you with the gravitational fields. Okay, so they kind of match up and come together. So as soon as we open the first page, you can see that diagrams look a lot like the gravitational ones, except for one important difference. There are two types of charge, only one type of mass. So charges can attract and they can repel, but the actual idea around them still works the same. Okay, now we've already picked up on this already, but electric field is a region around a charged body, so a charged object itself, where any other charged body will experience that force. Okay, so it does mean that actually, as long as we have two charges, then there will be a force attracting or repelling them, just like we have two masses causing it. Now we have an exact analogy because Monsieur Coulomb, he of Coulombs Law, came up with an equation that basically represents that equal and opposite force. Very, very similar to Newton's gravitational law, except this was done through mathematical and experimental research rather than hypothesis. But we still have radial fields, ones that radiate outwards in a circle from points. Where does that go to and from? They go from point charges, so the centre of charge of the object, which for most of our stuff is going to be circular, so we can think about that. And again, we have the idea of field intensity, field strength, so how intense the lines are. Okay, so again, represented in the same way as gravitational fields. And similarly, just like the gravitational fields in chapter, I can't remember, it was so far back, but when we did about motion in year 12, we can also get nice parallel fields. Now, I'll show you in the lesson, it's a bit more complicated where it comes from, but basically, if you have parallel plates, you are going to form a parallel electric field between them. And things moving through that, which experience the force, any charge, will just move in the same way that a mass experiencing the force due to gravity will also experience. So we'll have curves, and up here, radial, we're going to have circular motion. So circular motion, parabolas, stuff we've studied before. Okay, here we go. Monsieur de Coulomb, okay, Charles Augustin came up with a fact through experimentation. He tied different objects. He found that like charges repel. Doesn't matter if they're positive or negative. If they are the same type, they repel. If they're the opposite charge, they will attract. So effectively, what we're saying is, if that was a negative, for example, and those were negative, then that's going to be the effect. the size of the force he found was that the force was proportional to both charges, Q1, Q2, and strangely enough, the idea of the distance between them. Okay, now in the diagram here, I've used R because again in the data book we have R, but it is the distance between the centres that matters. Okay, so yeah, we'll stick with that. So we'll stick with the D. What he then did was he did more experimentation. He managed to measure the size of the force, and you got a bit of a hint of it in your practice the other day, multiple choice question, repelling charges on strings and things like that. You can measure angles quite easily. So what he found was there was a multiplying factor that went with his two bodies. Again, it doesn't matter on the mass of the bodies, it's not to do with that, it is the separation squared, but again we'll use this idea here. Now, because it's a radial field from a point charge, just like a radial field from a point mass, we can see that it fades out in the same way, which is an inverse square law, just like it was with the force on those. How do we find that? Well, it's to do with the surface area, that buttergun effect of spreading out over 4 pi r squared, the surface area of a sphere. So what he found was actually that force equals 1 over 4 pi r squared, okay, it's the surface area, and a multiplying factor known as epsilon, okay, or given the symbol epsilon, which is known as the permittivity of free space. Now be very careful about this. You won't need to come up with the phrases, but you need to make sure you understand it. Permittivity of the material the electric field goes through. When we get to talk about magnetism, it's permeability. So it's a very similar sounding thing. But yeah, permittivity of free space is effectively how well that energy transfers through the mechanism, okay, through the material that you've got there. So if you put something in the middle that's an insulator, you basically make that much bigger, okay? So what it does is it reduces the, should we say, the flow of that energy. Now, just to be aware, you might be given a bigger version. You might just have epsilon rather than epsilon naught. Epsilon naught is the permittivity of free space, okay? If you have a material that's 10,000 times stronger, you just multiply by 10,000. Now, a little hint for the exam. Hint. Okay. 1 over 4 pi epsilon naught, so for a vacuum, is approximately equal 9 times 10 to the 9 in terms of multiplying factor. So a 9,000 million, but 9 to the power of 9, quite symmetrical. It's 8.99, but it's close enough. Now that multiplying factor here gives us the same form as the one for big G in gravity. Big G was 10 to the minus 11, which kind of gives you a hint that electrostatic forces are so much bigger than gravitational forces, hugely bigger. Okay, so that's something we'll pick up to when we look at the forces that cause them, the actual quantum mechanics behind them. But yeah, gravity is so much weaker than the forces which, strange enough, hold your atoms together, which is good, because otherwise gravity would rip you apart, wouldn't it? So, yeah, the basic idea is nice and straightforward, and what we'll do is we'll use the same kind of modelling in that we'll use the version where we're going to consider that the force is created by, and I'm just going to use epsilon here to make it more similar, rather than epsilon naught, so whatever that is, large Q charged in a field, a test unit Q placed in the field at a distance r from it. Okay, so our test unit charge, think of that as 1 coulomb. It makes it much easier. So, likewise as we had before, we've got field strength. This time it's electric field strength. Well, from our definition that we had before, force per unit mass, this is force per unit charge. However, it is a vector, so which direction is it? And it's a direction on a positive charge. So if I take this back to this diagram, these arrows are the direction any other positive charge will disappear. So it will go that way. Okay. Now, in my little cartoon at the beginning, the reason they're saying, oh no, is we only realised this was the wrong one. We discovered 250 years later that they're really electrons. So, strange enough, most of your questions will be about electrons, and electrons will go against the flow line, okay, so against the field lines. So, the direction of the force, okay, depends on what the charge is, and that's why it's far more important to talk about electric field strength, okay, which, being electric fields, is given the symbol E, okay, capital E. So let's talk about direction of fields. We need to keep talking about field strength rather than forces, but if we go to our definition, then all we need to do is multiply that field strength by that charge and you get the force. So profound equation is the idea of force over little q, just be careful there, so that's a capital E, force per charge, okay, and that's your little q, and that's at any point in the field, independent, nothing to do with get me English right, of shape of field. So that field strength is at any single point, and it's how big the charge is. So force that you can measure depends on that charge, but it depends mainly on the field, which with a little bit of simple mathematics means that the field strength equation, again, F and E look similar, be careful. E, again, it's in the data book, 1 over 4 pi epsilon Q over R squared. Just like we had multiplying constant times by mass over R squared for gravitational field strength. Okay, however, that is just for radial fields. Okay, so very, very, very important, whereas that is for all field shapes. Okie dokie. Various units we can work on, but the easiest one I think for most people will be force per coulomb, newtons per coulomb. Okay, now you should be able to complete this. You can start the video now and fill this in, but let me give you an example. We have lots of similarities and differences with gravitational fields. So a lot of the ideas are similar. Okay, you can have the same shape of equation, so inverse square. Law for the force, you know, equations have the same shape, etc, etc, etc. So there's a whole load of possible things you could say there, but the main thing is the differences. Okay, so you have for gravitational, mass versus charge for electric. Okay, so that's your E field, that's your G field. What else do we have? Well, we have that multiplying constant. So the mass was basically 6.7 times 10 to the minus 11, whereas this is basically 9.0 times 10 to the 9. So it's, you know, it's huge in comparison, 20 zeros times bigger. Okay, they're both so far vectors. Okay, but again, the size of the vector is one thing. So let's just put versus so we can see it. Gravity, what does it do? Well, we have two field shapes because, or field directions, because this is always attractive. Oops, excuse me. Gravity attracts versus attract, repel, depending on the charge. So there's a single property. As I say, you have your mass, and it's worth putting in two charges. Okay, so there's two types of charge. What other things have we got? Well, again, definition of field strength is useful to kind of link them together, but G equals F over M versus E equals F over Q. Okay, so this, I don't know why I've written a D there, excuse me, that should be an L, repel. So those are your main differences, but actually very, very, very many similarities. Okay, so get to work on that. When we do the ideas that go on further, we can put them in. So there are things like work done, which gives us potential difference. Makes a lot more sense when we're talking about electric fields so far, but we also have potential difference there, etc. So inverse square law for force and field strength, just put that in. We have, oh, excuse me, we have the idea of potential. Okay, radial versus, so let's just put radial and linear. Okay, so shapes, depending on how it's formed. Okay, excuse me, shapes, depending how it's formed. So, big idea, but actually, as we do more and more of this, you'll see how this goes. So, lots of background explanation in the PowerPoints and in the lessons, so have a look at that more. Okay.